Let us look at another composition of gates, and this is really important because this will create entanglement. So we want to create entanglement. And when we say create, then from states where there is no entanglement initially present, and in particular from the computational basis states. The basis states are products of qubits in definite states 0 or 1, so there is no entanglement present in them. But we can create entanglement by the following combination of gates, which I'm first going to denote graphically. So we have 2 qubits, and then we are first going to apply a Hadamard gate to one of them, namely the first one. And secondly, a controlled NOT operation where the first qubit is controlling what's happening to the second qubit. I'm going to show you how this works in 2 different ways. In this first one, we simply follow the fate of the qubits throughout this circuit. So we start out with one of the computational basis states, for instance this one here as indicated there, and there the first and the second qubit are both in the state 0. And now the Hadamard gate will transform the first quantum bit into this state. And now when we think about what this means at this state for the composed system, this is really this combination here. And this is still before the controlled NOT operation. This controlled NOT operation tells us to change the state of the second qubit, but only if the first qubit is 1. So when we look at this state here, this will happen exactly in this case. So our composed system is then in the following state. And this can no longer be written as a product of 2 states, it's an entangled state, and this is indeed one of our Bell pairs. So while at this point we can still write this state as a product, it was just useful to write it here already as a composed system, because then when we work out the action of this controlled NOT gate, we will end up in a state that cannot be written in this way anymore. So we cannot write specific states down here and interpret the final result as a product of such states. We can only really talk then about this state as the state of the composed system, and this is really the manifestation of entanglement. Now one can see that all the other computational basis states will also become entangled states, namely the other 3 Bell pairs. So we have seen that this state here is being transformed into the Bell pair beta naught naught. Well, this one turns out to be transformed into beta naught 1, the next one into beta 1 naught, and this one here into beta 1 1, which explains the meaning of these indices. So these indices tell us how these different Bell pairs can be obtained from the different computational basis states using this very specific circuit, which we call the entangler. I said that I'm going to show you 2 ways how this works. So here is the second one. And for this, we are just going to multiply matrices. As a matrix, the Hadamard gate acting on the first qubit can be written in this block form here. And the controlled NOT gate can be written in this block form. And now we can see how this works by simply multiplying these matrices together, but we have to do it in the correct order. The Hadamard gate is acting first, so we have to place it to the right of the C0 gate, which acts second. And now we can multiply these matrices. I pull this factor 1 over root 2 to the very front, and then we have 1, 0, 0x from this controlled NOT gate, and then the remainder of the Hadamard gate, which is a matrix. So this looks like this one here. So we can work this out now by matrix multiplication. And here this really looks like multiplying numbers because we have so many identity matrices for which the multiplication order does not matter. And the result takes the following form. Now we can translate this back into a 4x4 matrix, where it will look like this. So this is really taking all these blocks. So here we, for instance, have an X matrix. You may have recognized that when I wrote down this result, I proceeded by the columns. And this is because when you multiply this matrix by one of the computational basis states, so basically a vector such as this one here, we are going to extract one of these columns, which one simply depends on where we put this entry 1 here. So for each of the computational basis states, we obtain a different result, but the different results are just the different columns. And when one now looks at the coefficients which appear here, including this overall factor 1 over root 2 at the front, then these are exactly the coefficients of the Bell pairs in the computational basis. So for instance, the first state here just corresponds again to 1 over root 2, the first computational basis state plus the last computational basis state. So this is beta naught naught. So now we know how to create entanglement out of non-entangled states. And for this, we use the Hadamard gate, which, as I said, is a very important gate for quantum computation. And the only 2-qubit gate that I said that we really need, namely the controlled NOT gate.